In this lesson, we are going to start discussing algebraic proof. As I've mentioned in class before, proof is one of the central concepts to working with geometry. And a proof is an explanation why something is true. Before we launch really heavily into explaining why a lot of the things in geometry are true, that is, before you have to explain why something is true when you're first learning it, it makes sense for you to learn the structure on how to write up proofs based on something that you already know, algebra. And so we are going to review some of the rules from algebra and use those as justifications to write up an algebraic proof. Furthermore, when we have equations, we want you to be able to represent and say, I recognize what this thing is. And so our first component that we need to address is what a proof is. Once again, a proof is an explanation. That explanation can use our rules of logic, our inductive and deductive reasoning that we've already been using. So there is structure behind the statements. If then, biconditionals. We will use definitions, we will use properties, we will use other things that we've already proven are true to address our explanations. In your previous notes, I had you take and get all of these pieces recorded. If you're watching on YouTube, you may want to pause the video and record all of these now. Just as a quick review, if you add on both sides, it's addition property of equality. Subtract, multiply, and divide. Basically, you have the collective golden rule of algebra. Whatever you do to one side of an equation, you have to do to the other. We also have the reflexive property. The reflexive property, quite simply, says 5 is equal to 5. And we can say that whenever we want. 20 equals 20. A number will always equal itself. The symmetric property let us take things and flip them around. For instance, if we know that 5 is equal to 4 plus 1, if we flip around the equation, it's going to be true also. We know that then we can flip equality and it'll still be the same. Remember, if you flip a less than symbol, this doesn't work. If you flip any inequality, that doesn't work. The transitive property is used for something like 5 is equal to 3 plus 2. 3 plus 2 is equal to 4 plus 1. And so we can chain through it to reach the conclusion 5 is equal to 4 plus 1. Lastly, we would have substitution. We know that if two things are the same, we can plug one in for the other anywhere. And so we also have the distributive property. Just quickly reviewing a lot of the things that you should already know from algebra. With the distributive property, if you multiply across the parentheses, you wind up with the expanded form. All right, so the first thing that we need to do, we have this equation 4m minus 8 equals 12. First things first, solve it. We know that our first step would be to add 8, which would give us 4m equals 20. Thank you. This is a negative 12, so negative 12 plus 8 would equal negative 4. From here, we could divide by 4, which gives us then m equals negative 1. For our algebraic proof, what we're really looking at doing is saying we have step number 1, we have step number 2, step number 3. Why are we allowed to do these things? And that's what we will have over on the right-hand side. We will create a list of justifications. What is it that we did, and why are we allowed to do it? What did we do in step number 1? Since we added 8 to both sides, What lets us do that? That was the additive property of equality. And yes, you can actually write out those words, additive property of equality, that's fine. But we will frequently use abbreviations just to save us some time with the writing. For the second one, what did we do? We divided. So what allows us to actually divide? The division property of equality. What did we do at the third step? We found the answer. Finding the answer, it wasn't in our list, but finding the answer is called closure. Closure just means if you do division, you'll get a number answer. If you do adding, you'll get a number answer. And I also would like to point out that this type of justification that we're doing is not a really, really super rigorous mathematical proof. A really rigorous, strict mathematical proof, this would be broken down into way more steps than 3. We are looking at it just as a general guideline, learning the structure behind a proof before we really develop the super strong rigor. For our second example, we want to answer the question, what is the temperature in degrees Fahrenheit when it is 15 degrees Celsius? Solve the equation for F, justify each step. So, this is a piece that we're starting off. Step number 1, we have the equation. Why do we know that this is true? We're given the formula. We're told this is the formula. Go ahead and use it. Because we are given that it's true, that's our justification why we know it works. What would we do next? Well, we can take advantage of this piece. When it is 15 degrees Celsius, we can plug that in to the formula. Why are we allowed to plug things into a formula? That is called substitution. In particular, it's the substitution property of equality. Whenever two things are the same, we can plug them in whenever we want. We can replace them anywhere. To continue the problem, what's the next thing that we would need to do? We could take the 9 over 15 times 9 over 15, 9 over 5.
Yeah,
There we go. If we take 9 over 5 and multiply by 15, that's going to equal 27. What is it that will allow us to multiply numbers? That's closure. The closure property of multiplication says multiplying two numbers will give you a third number. Lastly, no, that step is not the multiplicative property of equality, because the multiplicative property of equality says you're multiplying both sides of the equation by the same thing. That's not what we did. We were combining multiplication, not putting it into both sides. From here, we need to actually add the numbers. 27 plus 32 gives us 59. Which property allows us to actually add numbers? That's closure again. When you actually add numbers, that's the closure property for addition. Actually multiply, it's closure property of multiplication. This particular component allowed us to, well, this is just a fact that we've discussed in our classes before. We already know that AB with the line in front of it refers to the physical object for a segment. We know that if we put a ray on it, we're talking about the physical object of a ray or the physical object for a line. And if nothing is written down at all, that is the format we use to talk about the distance from A to B. It will be really common for us to treat something like AB as one variable. This can be one unknown length, and so we will treat distances a lot like we would treat a variable. This is not talking about an unknown variable A times an unknown variable B. Based on the context, you will have to get used to the fact that we can sometimes use two letters to represent one. For instance, we need to solve this equation for x. What would we start off with? What is the first thing that we know is true? This, of course, is getting back into our previous unit because we've done problems like these. In particular, we discussed that we could take a piece plus a piece, and it will equal the whole. Taking that approach, we can represent this with the first piece, the distance from n to m, added the distance from m to o, and that combined distance is from n to o. This, of course, is something that we worked with in our previous unit. And that was called, give me my right color here. We know that this relationship is true because the segment addition postulate says it will be. Now that we have these components, we can change it from having distances nm and mo, and we can start putting pieces into it. In particular, come on, give me black here. What distance is nm? That's 2x. What distance is mo?
Yeah, 20.
What distance is no? And those pieces, we're able to put them in. Why? What did we do there? That step is substitution. Substitution is one of the most widely used steps that we can possibly have. Replacing one thing with something else that's the same, we will use it constantly throughout the entire year. You absolutely need to know the name of substitution. It's never going to go away. Well, now that we have these pieces, we've taken the segment addition postulate for the geometry, we've done the substitution step, and we've created an equation. Now we're back to Algebra 1, so we can go through and start to solve. So what are we going to do first? We do need to combine like terms. And here's a part that is going to drive you guys absolutely crazy for how long it is to write something up. When you were in algebra, we'd simply take 2 plus 3 and get 5x. That's skipping a lot of steps. Yes, it's combining like terms, but combining like terms had some components there that you never write down in algebra. While we are learning proof, You will need to write these down so that you can develop an appreciation for step by step by step. It will make it long, it will make it tedious, and I'm sure you're going to look at it and say, God, Fry, this sucks. Why do we have to do it this way? Because this is what proof requires. We need a thorough, step-by-step explanation why things are true. Eventually, we will be able to create theorems which will act as shortcuts, and they'll make it shorter and shorter and shorter work. But since we have not done those yet, we can't use things that we have not created. We will go through and create a combining like terms theorem, and then we'll be able to use it. We don't have it yet, so we can't do it now. We're stuck doing it the long way, where we need to recognize we could factor out using the distributive property. We could factor out the common x. After factoring out that common x, using the distributive property, then we're able to put those two numbers together. 2 plus 3 gives us 5. And so we can write down 5x minus 9 equals 4x minus 4. And there we combine the numbers with closure of addition. Yes, in algebra you would have simply said combine like terms, and that would have been one step. We'll get to that point as well. So now what? What would you do to both sides of the equation next? Right? One thing we can do is add 9. After you add 9, you have 5x equals 4x plus 5. And that was the additive property of equality. Even though officially we did skip a step of applying the additive inverse, and we skipped another step of using closure. We actually skipped 2 steps there, but we'll get to that level of rigor down the road. Right now we're working on some of the structure and building to that point. What now? What would you do next? From here, we could subtract 4x. Five minus 4 would give us 1x. So it gives us x equals 5. And again, officially we have skipped steps. With this number 6, we use the subtraction property of equality because we subtracted from both sides. Officially, we did skip more steps. Again, I want to keep emphasizing we will build in complexity and build into a really rigorous proof where we don't skip anything at all. Right now, we're focusing just on the structure. And the structure for this proof is trying to explain, we have all of this work with recognizing the segment addition postulate, building the equation, running through the algebra, and solving the equation. Every step along the way, though, we're writing down in this right-hand column a justification. Why is it that we know this step is allowed? Why is it that we know doing this step is going to keep things true? That's what these justifications do for us. The left-hand column is a list of things that we know are true. The right-hand column are a list of reasons why we know they're true. Going back to our first unit, we discussed segments that are the same length or the same or are congruent. Well, we mentioned that from the reflexive property of equality, we know that 2 distances are going to be the same. And we mentioned before that if two distances are the same, we wind up with congruent statements. All of these pieces for the reflexive property of congruence, the symmetric property of congruence, and the transitive property of congruence, each one of these are just natural extensions of the reflexive, symmetric, and transitive properties for equality. Because if the relationships hold true with equal numbers, and then equal numbers cause congruent segments, each one of these things will be true for congruent segments too. And thus we want to build on these and start recognizing what we can do with them. Please remember our symbol though, numbers are equal, segments and figures are congruent. Thus, which property is this? Just looking at A. Angle QRS is congruent to angle QRS. Is this reflexive? Is it symmetric? Or is it transitive? This one is the reflexive property. So we have the reflexive property of congruence or equality. Reflexive property of congruence, because we are using the congruent symbol. What about the second one for B? Measure of angle 1 equals the measure of angle 2. So we flip them. Measure of angle 2 equals measure of angle 1. That is the symmetric property. And since it's equals, it's the property of equality. What about the third one? AB is congruent to CD. CD is congruent to EF. So bridging it, that is the transitive property of congruence. Lastly, for D, 32 degrees equals 32 degrees. That is the reflexive property. Congruence or equality. Because we're working with an equal sign, having equal numbers, it's the reflexive property of equality.